the 7-day technical session arranged by Scope in association with Spark. Wish you had a great weekend, even though the entire India is under the lockdown, because we are going through a bad phase of the humanity. Maybe all of us, those who are alive as of today, have never ever came through this sort of a phase of a life where we are sitting in our within our home, the four walls of our home, for last almost 50 days. Today, almost 44,000 plus people are undergoing treatment. This is not that much. We should not lose our heart that, oh, it is 44,000 undergoing the treatment, what will happen? But we should concentrate on the fact, though we have lost 2,200 plus lives in the fight, but there are another 21,000 people who has won the battle with the corona. So we should not look onto those 2,200 peoples. We should look forward for those people who has won. We should look into the brighter parts of our life. So looking forward for a good future of the entire industry and the entire nation and the human being. Let us start today's session. Today we are going to discuss on the partial discharge measurement of various substation equipments and different test equipments, whatever is available in the world or in the industry. Today I am having my colleague Mr. Jayant Dev available with me, who is going to discuss mainly on the partial discharge. He is the product expert. To take us to the journey of the partial discharge. So, without taking much of the time from Jayant's kitty, let me hand over the mic to Jayant. So, Jayant, over to you. Thank you all.
Thank you, Nilay sir. Good evening, everybody. Hope you guys are taking a good care of your health. Now, let's go forward. Today, we will be talking about partial discharge basics and what this phenomena denotes and how exactly how exactly do we deal with this particular thing. So, let's see how the itinerary is going to be. So first of all, we'll be looking at the introduction, then we'll see the byproducts of a discharge. Then we'll be looking at the types of partial discharge. Types of partial discharge. Then various PD testing methods. Then recommended sensor application, frequency band and sensors, basic terminologies that are involved in partial discharge measurement. Then product mapping and product offerings of ours. And in the end, we'll have our Q&A session as always. So let's go forward. So what is partial discharge? So IEC 60270 defines it as localized electrical discharges that only partially bridges the insulation between conductors and which can or cannot occur adjacent to a conductor. So the basic things that we have to take out of this particular definition is, first of all, it is a partial discharge, that is partial plus discharge. A discharge that has yet not broken down the complete insulation strength of the insulator. That means it is happening somewhere inside the insulation or on the surface of it that has yet not bridged the insulation level. Now, there are 3 points that are written right here. These are of prime importance. First one is these are localized electrical breakdown. That means these are actually the discharges that start happening at the physical defects at a very small level, that is at a very microscopic level, and they are at very primary level of their inception, right? Second, they can be inside or on the surface of the insulation, as I said while in the definition. So they can be inside the insulation, or they can be on the surface of the insulation. Now, last one is the high voltage stress. What exactly does it mean is that we are trying to, with this definition, what exactly we are trying to say is, with high voltage stress at these physical defects, the defects that are inside or on the surface of insulation, they give out these discharges. Partial discharges start occurring only when you charge these areas with high voltage. This is why the term high voltage stress has been written over here. So with this idea, we'll move forward. Now, what are the byproducts of partial discharges? By this, what we mean to say is, first we saw what partial discharges are. So they are physical defects that turn into partial discharges, or that show you discharges or the signs of discharges when high voltage stress is applied on them. Now, when it is applied on them, discharges, they give out something, just like any other discharge that we get to see in our day-to-day life. To give you an example is when we light our matchsticks. So whenever we light our matchsticks, it is basically a chemical reaction, but it is the most suitable example that popped up in my head. So let's see what happens when we lit our match. So basically, we get to see the light of the flame. Then we know, as we have burned it, or as we have ignited it, it is quite hot. And then we get to hear some smell. Sorry, we get to smell something, some odor is there, right? Because of the chemical reaction, as well as we get to hear some noise that your match has been lit. So as soon as that particular candle of yours, it catches fire, that stick of the matchstick. So these are the same things that has been discussed over here. Like, first one is light. So whenever there is a partial discharge, there will be light, of course. But the problem with this light is the chances of discovering this light, or chances of seeing this light, is quite less if the partial discharge is happening inside the insulation. All right. Second one is heat. When, as we discussed, whenever there will be partial discharge, that means high amount of heat dissipation in a small amount of time, right? So at that time, there will be hot spots that can be detected, or infrared radiations coming out of the hotspot that are detected by thermography that is already available in the market. Now I'll be switching to this last one. There is one more thing, the chemical reaction that takes place whenever the partial discharge is there, because we have insulation of different kinds, like you have epoxy kind of insulation, you have ceramic kind of insulation, and whatnot. So some chemical reaction is always taking place, and to counter that, or to take care of that particular thing, we use gas analysis methods. Like in case of transformers, we have got our online DGA, or we have got our DGAs. And in case of GIS, when the fluid is there, in case of GIS, you have got your gas analyzers, right, to detect if there is any gas like SO2 or something coming out of it. Now, these two methods, they are of prime importance here, and these are the two methods that we will be discussing today. Now, acoustic and electromagnetic, these are basically the sound waves, or basically the waves that will be coming out of the source of the partial discharge, or coming out of from the physical defect, which is under the high voltage stress. So these are of two kinds, acoustic and electromagnetic one. Acoustic one, they can be audible or inaudible. By inaudible, we mean to say these are ultrasonic waves. That is, the frequency of the waves coming out of the sources are above 20 kilohertz. So ultrasonic waves are there. We'll see them in detail, so don't you worry. I'm just trying to give you a brief idea about the kind of thing that we are dealing with. Now, electromagnetic are again the waves of electromagnetic frequency ranges that are coming from the source of the partial discharges. They are basically transmitted UHF kind or induced TeV kind of waves. Now, moving on. Now we'll see what are the different kind of partial discharges, or the different kind of defects that we get to see when we talk about partial discharges, or what leads to the partial discharges. Now, the first one is floating potential. Floating potential is basically they are foreign or loose objects that are inside the insulation. So here, as you can see in the diagram, here you have got some bushing, which was supposed to be grounded with help of, this is just a schematic. So you can suppose this is a support insulator, and this particular bushing was supposed to be connected with it. But here, either the connection is loose or the connection is totally gone. So it is totally a loose wire or disconnected wire. Now, due to this particular thing, what happens is, in this particular area, as if you can recall, the equation of electric field, it is E equals to V by Q. That means electric field is equals to voltage applied upon the charges accumulated, or sorry, the distance between them, right? So what happens is, as you have created some distance, or you have disturbed the electromagnetic equilibrium of this particular area, of this particular insulation. So this leads to this, loose connection. It leads to ionization in this medium. And as we are dealing with AC, that is alternating current, so with change of the polarity of our signal, the charges keep on jumping from one source to other source. By one source of other source means when the contacts are loose, both are basically the sources, right? So in positive half, let's say this particular terminal, it acquires positive or high voltage potential. So the charges will start jumping from here to here. And in negative cycle, this will acquire negative charge. So the charges will start jumping from here to here. So this jumping of charges, the spark that we commonly call whenever there is a loose connection, is what the floating potential signifies. Now they can be manufacturing defect, and in most of the cases, more than 70% of the cases, they are because of the human error while doing the maintenance, or while doing any work with your equipment. If somebody misses out to connect the cables properly, or connect the joints, or connect the terminations between the two particular mediums properly. So this particular phenomena starts happening there. Now it is one of the most common partial discharges, and one of the severe one. That means if you are having floating potential, which is a very common phenomenon, as I told you, that due to loose connection you get to see this, which is a very common scenario in our substation or in case of any equipment. So you don't have to worry too much about it. And how we will be taking care of that particular thing, or what should be our next course of action, that we will discuss later. Now this was floating potential. Second, we have got void discharge. Now void, as you can see here in your solid insulation, it is an air bubble, or air void that happen inside solid insulation. So here C point, it denotes a void. Now what happens is, in your perfect insulation, when there is no defect, you have got a capacitance. We usually denote our insulation with a capacitance value. Now, due to its dimension and all other aspects, you have got your C, capacitance. C is equals to epsilon naught, epsilon A by D. Now, everything is defined, and you designed your system accordingly. Now, because of this air bubble, your this particular insulation, so suppose it was epoxy. Now here, it is not epoxy, it is air. That is, your value of C, it got changed because of epsilon, and then it has got a dia, and it has got its own dimension. So the value of capacitance of the C will be something else. Now the value from the top of C to top of HV to the bottom of HV electrode, that is B at the top, and there will be a capacitance in the bottom B. So the three capacitance are coming into series here. So overall capacitance will be 1 upon equivalent of this capacitance, 1 upon equivalent of this capacitance, and 1 upon equivalent of this capacitance. So overall capacitance will go down, because in series capacitance, the equivalent capacitance is reciprocal sum of all the capacitances. That means your insulation strength goes down due to the void insulation. Now they are void insulation. Of course, void cannot be formed at the site. They are generally manufacturing defects, which are found in solid insulation, as we said. So they are found in cables, bushings, GIS, junction insulation. They are highly destructive. By highly destructive, what we mean to say is, if they form, they are irreversible. Their effect are going to get worse by day. You might not be able to see it in 5 years or 10 years, but sooner or later it is going to turn into some insulation failure, or this may lead to some complete insulation failure. So that's why we call it highly destructive, because they grow until the failure. So this is the second kind, the void discharge, that happens inside the or on also on the surface of the insulation. Now you have got floating particle. Floating particle, as we saw one example, we saw one kind which was floating potential. This is somewhat different from it. These are microscopic particles. Floating particle it is, right? So these are microscopic metallic, non-metallic particles that are inside the fluid. That means in terms of fluid insulation, we have got oil as well as SF6. Now here, as you can see here, these are small metallic particles or microscopic particles. That generally are inside, that generally don't, that are taken care of while designing or during commissioning tests. But somehow, let's say some particles are left inside the GIS or inside the transformer. So they particle, just the equation that we discussed, E equals to V by D. Now, due to that, around these particles, ionization occurs, and these particles actually, due to the AC nature or alternating nature of our voltage stress, they keep charging and discharging, right? Now, on their own, they are not very dangerous, but if they are near to any insulator, mostly the support insulator that you have inside the GIS to support your conductors or the insulation barriers. So if they are in close proximity to those insulators, they will cause immense damage, because slowly they get embedded in those surfaces, and discharging slowly grows into something else that we'll see, that it mostly turns into surface discharge. Now you have got, if they are there, you cannot help it, but you have just one solution left. If they are ever detected that you have got some floating particle inside, or some contamination or dust particle inside your fluids, or in most of the cases your GIS, you have got only solution left is to purify and process the oil. All right. So this is the third kind, floating particle. Then comes our surface discharge, which is also called tracking. Now, what that means is, this is, I think, the right diagram, the picture in the right, is something that we have encountered every now and then, as you guys are, most of you guys are working in the substation. This is quite a prominent view, unfortunately, with the switchgear panels. So what happens is, these are the discharges that happen on the surface of the insulation. So what happens is, whenever there is, let's say, some dust accumulation on the surface of the insulation, or let's say some water ingress on the surface of the insulation, that particular, you can say, violation of the insulation strength, it start, suppose water ingress happens. Let me tell you with this particular example. If water ingress has happened, so that particular water over the time will get vaporized, but it will leave carbonized tracks behind it. All right. These carbonized tracks are the contamination that was carried by water or something else, but they will give a resistive path for the leakage current or the discharges to bridge the gap between the insulations or the insulators that we have, which can turn into flashovers on the surface of the insulators, or you can also see these kind of things happening just on the surface of the insulation, or this kind of thing happening. So as you can see here, the tracking happens all the time. So this is how the surface discharge happen. They are the discharges that happen due to water ingress, dust, pollution, or for any other reason on the surface of the insulation. So they tend to track along the grounded metal, that is towards the ground. They always try to, anything that is getting discharged, it always tries to get grounded or move toward the ground path. So this is one type, surface discharge or surface tracking. Next is corona discharge. This particular phenomena does not require any introduction, as it is again one of the most prominent views that we get to see in our substation. Now, they are the discharges from surface to air, surface of the conductor to air. The reasons are because of the unevenness of the surface, or the sharpness of the surface angles, or bending of the conductors at the wrong angle. So at those particular points, the electric stress at these particular points increases beyond the dielectric voltage strength of that particular area, of that particular insulation in that particular area. And then these discharges from the surface of the conductor to the air starts to happen. They are generally recognized by their bluish or violet glare, as you can see, and the humming noise that comes out of it. These discharges, they turn into surface PD as they become more severe. The example that you are seeing here, it is not because of corona, but it is because of the surface discharge that occurred. And that surface discharge that occurred, which was initially corona, but due to, because proper action was not taken on time, this is the kind of thing that happened over there. And this particular case, as you can see, it is not a surface discharge, but it is due to corona glare, or due to the presence of corona on the just at the tip of the insulator. So this was all about the PD types. Now, now the question comes: why do we need to test PD when so many PD testing methods are already available in the market and people are actually using them? Now, with PD testing, there are some added advantages like the ease of locating problem that may or may not that may occur inside or on the surface of the insulation. So PD testing is one of the methods where even when your system is running, whenever your system is working, you don't need to take any kind of shutdown. So this is one thing that is one of the things of prime importance with PD testing. And you can locate your problems, pinpointing the problems. This is one added advantage of PD testing. Then it mostly is a predictive analysis tool. By predictive analysis, what we mean to say is, suppose a defect is detected. We have already detected it. We know, yeah, some partial discharge is happening. Let's say some corona is happening or some void kind of discharge is happening over there. Now, due to one reason or another, because it is not actually very feasible for us at the substation to take the shutdown more often than not. So what we do is we put that particular area or put that particular area of the insulation or that particular case in our monitoring system or in our monitoring. We continuously monitor it whether that particular defect is getting worse or that particular condition is same or it is getting worse. So by doing that, we get to see whether things are going bad or not, or if it is going to turn into something bad or not by doing the trending of the data. So that's why it is a predictive analysis tool. We can actually predict, or we can actually see if it is going to get bad in some years or not. Now it has got alarm system. Of course, if the things are going bad and you are monitoring it on a continuous basis, you can easily using this predictive analysis tool, you can always have an alarm system to alarm you, people. Yeah, the rate of increase is too much, or the rate of increase is too high in your system. Now it is an online testing system, as I said, so it does not require any shutdown. So these are some advantages of PD testing that are not actually found in most of the tests. So now next is we are testing PD. That is fine. The reasons are mentioned over here. Now what to test? When we say we are doing PD testing, now what exactly to test? So the first one is PD type. All right, PD type is the types that we saw. Which one of it is? Because we saw in the earlier slides that PD, depending upon its types, has also been categorized in various severities, like corona and floating potential. If you can recall, I said they are of least severity because they was there, and they are not something that actually cause too much of a trouble with your insulation system, even if they are. Although if they are, you must always be aware or you must always be monitoring them if they are there, that they are not getting or they are not turning bad over the time. Now, second that you need to observe is your magnitude of discharge pulses. That means what magnitude is it? As I said, in the predictive analysis tool, we get to see the change in the magnitude. Now, because of a lack of a IEC, IEEE, or any known international standard that says yeah, a particular discharge type of a certain magnitude is bad above or below a certain magnitude, that particular data is not available with us because the because of some reason best known to these standards. Now, what we do here is, if we have one magnitude, let's say we have got one reference magnitude, we took one value. After that, we do the trending. That yeah, at a day it was 65, then it increased by 10% or decreased by 5% or increased by some other percent or decrease. So like that, we do the trending. So that's why we need to take care of the magnitude of discharge pulses. Then comes the pulse repetition rate. As we are dealing with the alternating voltage, so our pulses, they keep happening over the time. These are actually rate of discharge pulses per unit second, the number of discharge pulses that you obtain per unit second because of the 50 hertz supply that we have over here. So this is also one of the important parameters to tell you if the discharge has actually gone bad, right? Although it is not absolute, the all points that I have mentioned over here, let me come to that after this. And also you need to know the discharge power. That means how much of the discharge, how much of milliwatt or microwatt of discharge had occurred over there. You should get all these data. Only then you would be able to see how much of a discharge, or how, after knowing what kind of a discharge it is, what is the exact status, or what is the status of the discharge, and what is the status of your insulation. So your analysis should comprise of all these 4 points, not just one of them or two of them. All of them, they comprise to give you a complete idea of the status of the insulation or the status of the discharge. Hope this is clear till now, why and what. Now, now comes the correlation with other tests. As I said, that already so many tests are there, then why people need to go with PD testing? So for that, we explained the reasons. Now, after having, let's say, PD is actually not a thing that people do firsthand. So first of all, let's say in the case of transformers, you have got your IC 10593 that has told of doing the DGAs in a certain method, or analyzing them with the methods that are available, the gas ratios, the dual triangle, and everything. Now, with the help of the faulty gas content, or the gas generation rate, or the insulation ratio that are there, or if you take dual triangle, it has also got one component of right at the very tip of that, you have got partial discharges. So you can always relate these data with partial discharges. People generally do the DGA, they see their the component ratio, rate of increase of hydrogen is too much, or the value of hydrogen is too much, or the value of, let's say, methane is too much. Then they go for PD. Okay, I think partial discharge is happening, and we must try to pinpoint it, or we must try to find out why exactly is that happening. Because pinpointing is not possible with DGA, or you take the case of 10 delta, they are not possible. So they go with partial discharges. Now, thermography is one more thing that is available over there. But there is one demerit with thermography as compared to partial discharge is thermography is useful only after your defect has gone so bad that the defect has gone so bad and the discharges are happening so much that it causes hotspot that can be measured by a camera by standing at a certain distance, let's say 5 meters or 10 meters. But with partial discharges, you can actually detect these defects when they are at their incipient levels, right? That means they are not causing or emanating that kind of a discharge or that kind of an energy that can cause a hotspot, happening of hotspot at those points. So, whereas these are some points that these are some methods that always are correlated with the partial discharges testings, or the location of partial discharges. Now, what are the steps you need to take? We already saw why to do PD testing. Now, how to do PD testing? What are the things that we need to measure when we are doing PD testing? Now, here we will see how to do it. Now, first of all, we need to understand there are some terms, or there is a, this is a analysis method that always needs to be adopted to get a meaningful or a something or a data that something can be worked upon. Now, first of all, we detect the partial discharge, whether there is a PD or not. All right. After detecting it, we are doing measurement. That means we are taking the readings of the magnitude of the pulse repetition, discharge power, everything we are doing here. Now, after detection and measurement, we must know where exactly it is. All right. So detection, after detection, it is very important to localize it. And localization is quite a feature of partial discharges. Then after doing everything, we have the option of having monitoring. We do the monitoring even after doing the localization. If, let's say, I don't want to take some action on that particular point, but I want to keep it under my surveillance. So you start monitoring that point. All right. And you do the trending of the data. So only after doing the trending, you can have something to work upon, something concrete that can be worked upon. So these are the steps that needs to be followed. First is detection. After that, detection, measurement, same thing. Then comes localization. Then after you have localized your partial discharge, where exactly in your insulation is the defect happening, then comes monitoring of the data, and then comes the trending. When you are monitoring it, you are getting trending of the data, and then you can use that particular tool as your predictive analysis tool. Now, what are the PD test methods available? Yeah. So PD test methods they are actually of two kind, and please pay attention as this is something that people actually confuse a lot. So PD testing are of two types. First one is offline PD testing method, and second one is testing methods are generally done in a very controlled environment, in mostly in labs or in the manufacturing utilities, where you have got Faraday cage and controlled voltage sources where you can fluctuate the voltage. You can change the voltages again and again so as to check the PD inception level or extinction level of the partial discharges. Now this kind of a facility might not be available for online PD monitoring. Okay, because here it is a non-intrusive method that we are trying to propose, or it is a non-intrusive method that is available in the market. They generally do not require any shutdown. They have to work on the system frequency, on a system voltage that is at a particular frequency, at a system frequency. So this is what we are going to talk about today. Not this is a totally different topic. Now, with online PD testing or on-site PD testing, you have got actually two methods. First one is portable, second one is continuous monitoring. I think you guys must have got an idea till now. The portable one are the condition-based or on-demand methodology kind of kits that you have. That means whenever, let's say we have a case of a transformer. I took DGA, and DGA shown that there is hydrogen or methane, or with the help of dual triangle, I can identify some partial discharges happening inside that particular transformer. So after that, I'll try to localize it. So I'll take my kit on the site or near that transformer, and then I'll try to localize it, right? So that particular thing is my portable one. That is condition-based maintenance kind of a kit. Now, second one is your continuous monitoring one. So in continuous monitoring method, we have got 24/7 monitoring system. That means I'll have my sensors installed in the transformers, on the surface of the transformers, wherever the point is or whatever the kind of sensor it is. And those sensors will be taking reading or be taking the data in a monitoring unit of mine. Right, and that data can be displayed anywhere as per the desire of the customer. Like if you want to see it in your control room, or you want to see it in your regional office, regional center, or wherever you want to see it. So that can be done. So I hope this is clear to you that PD measurement are two types basically. First one is offline one, second one is the online one. Online one is the topic that we will be talking about today. Here, it does not require any shutdown of the system. It is on the live basis, with the help of the sensors that are quite safe to use with. So it is not like you are putting yours or anybody else's life in danger, right? So we'll see the kind of sensors we'll be dealing with. So first one in this on-site one or online one is portable one. Second one is the continuous one. In portable one, the portable one is the portable one that is carried every time I require a PD testing in the site or in the field. The second one is the continuous monitoring one. That means the sensors are already installed and continuous monitoring with the help of my data acquisition unit will be done. Now moving on. Now this is the wave emission technique. These are the online PD test principles that we apply, or these are the principles that come into play whenever we try to do the online PD measurement. Now, as we saw, we have got two methods. First one is condition-based maintenance method, that is portable one, and second one is 24/7. Now, these are the sensors and this is the technology that takes into account. Now, let's see them in detail, what they are. So, in wave emission technique, as I said, as we saw in the earlier slide, or for one of the few slides in the beginning, that whenever there is a discharge in the physical PD, defect, whenever there is a partial discharge, it will emanate sound, or it will emanate some waves, right? So these are the waves. First one is acoustic, second one is electromagnetic. These are the two broad demarcation of the waves that will be coming out of it. So the acoustic one has got actually two kind of sensors that are commercially available in the market. right? These are very generic terms that we will be going through so that you can get acquainted with the solutions that are available in the market that will help you in the long run. So first one is the airborne sensors. These are non-contact type dish kind of a sensors, right? The ultra dish kind of sensors that we use. We'll see all different kind of sensors later in the slides. Just this is just for your information and to get an idea basically. Second one is the contact probe kind of sensors. These sensors required to be put on the surface of the insulation or on the surface of the equipment that you are trying to do partial discharge analysis of. Yeah. So in acoustic, you have got two kind of commercially available sensors or available sensors in the market. First one is airborne probe or the airborne sensor. Second one is the contact probe or contact kind of sensors. Now, electromagnetic waves, they are further differentiated or demarcated into three types. First one is high frequency, then very high frequency, then ultra high frequency. Okay, easy, I guess. High frequency, very high frequency, ultra high frequency. In high frequency, you have got two kind of sensors, HFCT as well as the coupling capacitor. So HFCT are actually clip-on kind of sensors. They do not require any kind of shutdown. They are just CTs only of high frequency. These are the CTs that capture waves or the signals coming out of your equipment at a very high frequency. So they are not your regular CTs that work on the system frequency. Second one are the coupling capacitors. These are bushing sensors of, you can say them bushing sensors of miniaturized version, right? So they step down the voltage and try with the help of, because they are coupling capacitors. So they also work in high frequency only, and they try to capture the signal or the PD waves that are coming out, the PD current that is coming out of that particular terminal or that particular point where the sensor is. Okay, and from the other terminal of it, you can take the reading. Now you have got transient earth voltage sensors, which are colloquially called TEV sensors. They come under the category of VHF sensors. In UHF, you have got three basic sensor types. Like first one is internal sensor. Now UHF internal sensors, the people who are dealing with GIS, they must be very well aware of it. That in GIS nowadays, people are asking for internal sensors. So just for the information of everybody, even if you don't know it, these are the UHF sensors that are placed or they are embedded in the GIS to capture the partial discharges. They are pre-installed. They are installed at the site only. At the site means in their factories, and then delivered to the customers. So, and they have a common terminal. So whatever equipment you are buying of partial discharge, if it is a UHF sensors, if it is pre-installed with the UHF sensors, let's say your GIS is pre-installed with the UHF sensors, you don't need to worry about its compatibility with any other kit. Most of them have a standard N-type terminal, and every kit will be compatible with this particular sensor. Now, external UHF sensors, these are inferior version of the internal sensors. Why I said inferior version is when you are putting sensors inside the GIS, the sensitivity is actually checked, and the sensitivity is actually very, very good. Whereas when you are using external sensors, you actually have to place these external sensors on the insulation barriers. Yes, and there the chances of the signal or the strength of the signal coming out of the GIS, the total reading depends upon it. What kind of a magnitude we'll be getting out of it, right? So the sensitivity of external sensor is quite low as compared to the internal sensors. Then comes the antenna. These are the UHF antennas. These are handheld kind of antennas that are, they are non-contact kind of a sensors, and they are just antennas. They are like the antennas that in earlier days or some couple of decades back, the kind of antennas that we used to use in our TVs, right? Extended and that kind of antennas. So we'll see how these antennas look like and what these antennas are. So this is a brief idea about the kind of technology available. So the technology is broadly demarcated into two types, acoustic and electromagnetic. In acoustic, you have got two kind of sensors, non-contact type and contact type, right? Airborne is non-contact type, and second one is contact type. Then you have got three more classifications like HF, VHF, and UHF. In HF, you have got two major kind of sensors. In VHF, you have got one kind of sensors, TEV, and then you have got UHF, that is And there you have got three kind of sensors: internal, external, as well as antenna. Now, as I said, these are the generic terms that you will get to hear every time you go out there to deal with any partial discharge measurement or PD testing. So just keep this in mind when you are dealing with any partial discharge measurement. Am I audible to everybody?
Yeah, Jayant, you can start.
Okay.
You can also
I
switch
beg,
off
I beg your pardon. I
your
believe.
video. It may take some bandwidth. So you can better switch
Yeah.
off your video and start.
Okay. Sir. Okay, I'm really sorry for the technical glitch. Now let's continue after this. Now the recommended sensor applications. We saw the sensors that are compatible with the kind of the equipment that you're dealing with. So we had seen the switchgear panels, then you have got cables. Yeah, so in cables, generally acoustic and HFCT technology or the sensors that are in this region are generally used. Then in GIS, you have got acoustic, HFCT, as well as UHF. So except TeV, almost all the sensors are compatible with it. Now, this is a very generic idea. This is no hard and fast rule. What kind of sensors are you going to use? Now, this is a recommendation, as there is no IC or any international standard that says that, yeah, you have to use this kind of sensor only. Now, the recommendations that are given over here are recommendations that are given by IEEE or SIGRE with help of or with the experience that their, the body that formed these recommendation panels, they had. So based on their experience, they came to the conclusion that, yeah, for this particular frequency or this particular equipment, this particular frequency is most suitable. Okay, because here what we are trying to do is whenever there is a partial discharge, all you are trying to do is you are hoping or you are trying to catch those signals coming out of that particular source, right? So you must be acting at a frequency range where the probability of occurrence of those partial discharges or the probability of happening or the probability of the waves to occur or lie in that particular frequency range is high. So on the basis of that, these recommendations have been made. However, it has again been pinpointed this way. As you can see in this slide, you have got your power transformer, you have got your instrument transformer, right? You can see the red ticks over here. So these are the most recommended one or most adopted one in the market or in the available technologies that there are in the market. So in case of transformer, be it instrument transformer, be it power transformer, acoustic technology is preferred to detect, pinpoint, localize the partial discharges. Now, when it comes to motors and generators, we use HFCTs or coupling capacitors. Okay. Then when it comes to switchgear panels, TeV is most suitable for this kind of an application of detection or localization of partial discharges inside the switchgear panels. Now, when it comes to cables, again, HFCT and coupling capacitor are most suitable ones. And in case of GIS, UHF is the most suitable. So this is just a rough idea or a rough sketch of how you should be looking at a particular solution whenever you are going out there to find one. Okay. Next, these are the frequency bands as we saw HFCT, RFCT, TeV, everything we saw earlier. Now we'll see in detail what exactly these are. Now you have got your AE sensors, that is your acoustic sensors. These are your contact kind of sensors. And all the sensors have been written over here and you have got your frequency ranges over here, right? Now in in acoustic one, you generally have three kind of sensors, right? As I said, you have got contact and non-contact type. In contact type, you have got this sensor, let's call it acoustic emission sensor. And these two kind of sensors are the non-contact kind of sensors, right? This is the parabolic antenna kind of sensor or dish antenna kind of a sensor with a concentric dish at the end and sensor right in the middle of it. And you have got ultrasound center frequency kind of antennas or sensors. Now comes high frequency sensor types. So first you have got HFCT, RFCT, that is high frequency CTs, or it is RFCT. These are just generic names. So it can be a high frequency CT or it can be radio frequency CTs. Then comes coupling capacitor. Coupling capacitor again is in the range of high frequency. So this is the range, as you can see over here. The acoustic sensors or the this ultrasound wideband one, they generally are from 30 kilohertz to 300 kilohertz. Then you have got the acoustic sensors that generally go from these acoustic sensors are from 2 kilohertz to 31 kilohertz. Then almost this acoustic band, it almost is in parallel with your audible sound region. It lies in there. Then you have your ultrasound center frequency kind of sensors. They generally work at a center frequency of 40 kilohertz. All right. Now you have got your high frequency sensors that generally operate from 100 kilohertz to 20 to 30 megahertz. Then you have got your very high frequency ones. They generally work from 10 megahertz to 100 megahertz. So quite a wide band frequency range. Then comes your ultra high frequency sensors or the ultra high technologies. So the frequency ranges that I'm telling you, they are again with the sense or with the recommendation or with the idea of the manufacturer that the probability of occurrence of the partial discharges in these frequency ranges is maximum. All right. These are again not hard and fast, but if you are working on these frequency ranges, you are playing actually quite safe to detect partial discharges, right? The probability of detecting those signals gets higher. So in UHF, our frequency range is from 200 megahertz to 1500 megahertz. So it is a radio frequency kind of a frequency range. Now we'll see them one by one, what these sensors are and how do they look like. I hope this is clear to you guys. If not, we'll discuss about them in Q&A session. Now, let's take up the case of acoustic sensors. Here, as we discussed, we have got two major kind of sensors, contact one. So this is your acoustic emission sensor. This sensor, as you are seeing over here, it is contact kind of sensor. These are commercially available. So the outer linkage that you are seeing over here, the black linkage, they are generally magnetic kind. So on any grounded metallic body like transformer tank, switchgear panel, or dead tank kind of a circuit breaker, anywhere where you have metallic grounded panels, there you can stuck these sensors on the body, and with the help of this connector, with the help of a cable, you can always take readings. So this is one contact kind, and rest all are non-contact kind sensors. Okay, the parabolic antenna that we were discussing about, that works in the ultrasonic center frequency range, right? Ultrasonic because it is above your 20 kilohertz frequency range, and it generally works at 40 kilohertz. So this is a commercially viable and commercially available frequency range. These are the two sensors, or these are the two antennas that you will get to see very often when it comes to ultrasonic center frequency kind of antenna. So here, this is a parabolic dish to concentrate the signals, and this is your sensor to take the readings. Now this one here, this has, as you can see, a nozzle kind of structure is here, so as to take this sensor to the remote locations, or the locations where you cannot reach, far-reaching kind of places you can put it and take readings. Now this one sensor, or this one particular instrument that you are seeing over here, this is actually the acoustic kind of this works in the acoustic range. The frequency of it is from 2 kilohertz to 31 kilohertz. And as you are seeing here, dots, these are actually sensors. 124 number of sensors are there on its face. And with help of the sound or the signal coming between 2 kilohertz to 31 kilohertz, it actually tries to locate the source of partial discharges with the help of these 124 sensors. So this is also a solution available in the market. So I hope it is clear to you guys. This AE sensor, it works in ultrasonic wideband, that is 30 kilohertz to 300 kilohertz, and it gets magnetically coupled on the surface of the metallic surfaces, the metallic surfaces that are grounded for the safety purpose. Then comes your ultrasonic center frequency kind of sensors. So these two guys take care of that. Then comes your acoustic sensors. So this particular solution takes care of it. All right. So acoustic is covered over here, all the solutions that are commercially available. Next comes the high frequency one. In high frequency, you have got two kind of sensor technologies. So first one is HFCT or RFCT, that is high frequency CTs or radio frequency CTs. And second one is coupling capacitor. So please don't confuse between HFCT and RFCT. These are generic names which are used interchangeably. All right, so there is no worry about using them. Now, there should not be a confusion actually between them, why it is high frequency, why it is radio frequency, because the electromagnetic wave, the moment you are getting into megahertz, you are already getting into the radio frequency. Okay, it is a broad spectrum. So that's why high frequency is also called radio frequency CTs. Now, these are various kind of RFCTs available. As you can see here, a lever is here, a screw is there. You can just take this screw out. It will get open. It is a clip-on kind of a CT, so it will get open. You can place it around the wire that grounds the sheath of the cables generally. That is the quite common application of it, or the earthing plate that grounds the transformer tank. So across it, you can place these RFCT without without any requirement for the shutdowns. And they come in various IDs and ODs. So as per your requirement, you can use them. Now, high frequency, as we saw, They have got frequency range from 100 kilohertz to 20 megahertz. So they all of them almost comply to that frequency range. Now you have got HFCT. So HFCT, as you can see here, as I was telling you, they are the miniaturized version of your bushing sensors. So here, as you can see here, this is your bushing, the conductor or the equipment that you are trying to use this sensor upon. It is brought in contact with this particular terminal at the very top of it. It is a pin kind of an insulator, pin insulator, as we know in the medium voltage transmission. So here, and here is your output terminal. Output threading is available here. There you can put your cables and you can take the readings. So this is how this whole system works, and this is what is available in the market in terms of high frequency sensors. So in high frequency, you have got CTs, high frequency or radio frequency CTs, as well as you have got coupling capacitor. Now moving on. Here is the TEV sensor, that is the transient earth voltage sensors, that works in the frequency range of VHF, that is very high frequency. It has a frequency range of 10 megahertz to 100 megahertz. All right. So these are capacitive kind of sensors which are placed on the metallic body of the of your equipments like transformers and switchgear panels. So they form a capacitive plate kind of a phenomena, or the capacitive plate. Basically what these are, whenever there is a partial discharge, these waves, these voltage or current signals, they generally come out and strike on these metallic surfaces, which then try to get grounded, as we saw in case of surface discharges. So when that happens, there is a region of voltage distribution, and with the help of the capacitance of these capacitors or these capacitive sensors, we sense those signals. Okay, so this is how this particular transient earth voltage sensor works, and it acts in a frequency range of VHF, very high frequency. Now this is also a commercially available solution that is given by almost all the manufacturers. Now comes UHF sensors. So first one is your UHF sensors, that is, these are two of your sensors available over here. This is one example of one internal sensors, and this is the external sensors that is placed on the surface of the insulation barrier, and this one is placed or embedded inside the GIS, all right, on the surface of the GIS, and this is done in the manufacturing area only. When the GIS is already at site, applying this particular method is quite tough. Now you have got UHF antennas. So in terms of antennas, you have got two antennas over here. This is called directional antenna. This is called stub antenna. There are two kind of UHF antennas that are there. That doesn't make much of a difference. Now they are, as you can see, these are antennas which are handheld and are to be pointed in the direction of the insulation where you want to detect the partial discharge that is happening out there. So these are used for substation surveying as well as your transmission line insulators. So these are some solutions that are available in terms of UHF antenna as well as your UHF sensors. All right. Now the frequency range is between 200 megahertz to 1500 megahertz. This is a wideband frequency range, and it is good enough to detect any kind of partial discharge that is happening mostly inside GIS, because this is the most preferred frequency range for GIS. Okay. Now moving on. Now, some terminologies that we need to understand, what partial discharges are and everything. Now, let's dive into the details of the partial discharges. What we want to, what exactly are we trying to detect here? So, first of all, that knowing the right type of partial discharge is very, very important. As you can see the screenshot here, you can see the cloud of discharges happening. Okay. Now, this is just one example of it. There can be so much of noise, so much of noise. In those cases, identification of partial discharges get very, very, very tough. All right. Unless you are a seasoned person or you have done enough PD analysis, it gets actually quite tough for anybody to understand what is the type of partial discharge. Now, the system of yours. So that is one problem that will be taken care of later. Now, this is one thing your system should always be capable of, is trying to know the kind of partial discharge, because having a reference signal or referring noise, as people nowadays are referring to that I require a reference noise for corona, I require reference noise for X, I require reference noise for Y. It is actually it sounds quite easy, but it is actually quite tough, because in substation we have got so much kind of a variety. So I mean, such a variety of equipments available. Now, every time knowing or matching these figures with the standards is not that easy. So your systems should be smart enough. It should be working on the machine learning kind of kits, or it should be smart enough. When I say that, it should be working on either your AI engines or your machine learning algorithms to identify the kind of partial discharge that is happening over here. Now, if you please, if you can look over here, just below the floating potential, the thing that I discussed with you earlier, that you must always know the amplitude of discharge. All right, where although this is not absolute, this has to be relative. That is, this amplitude on its own is nothing. You require 2, 3, 4 data to tell something about the magnitude of this discharge, because there is no IEC standard as such that tells what should be the magnitude of a good discharge or a bad discharge. So you need to know the amplitude. Okay, then you need to know the power. That is the total discharge power that was sensed by your sensor. Any of those sensors that you saw earlier, that we have seen earlier, all those sensors, they detect the discharge power, of course. From that only this voltage is being calculated. Now, out of that power, as you can see over here in this description, 95% of total power, which means the discharge power that was detected, or the total discharge waves that was received by the sensor, that was measured by the sensor for the given time. Let's say you took the reading for 1 minute or 2 minutes. So this is the total discharge that was obtained. And out of it, 95% of the waves that were received are of PD type. All right. That means 5% is noise and 95% is floating potential kind of discharge. And as this system, it works on the AI engine, AI algorithms, and the system is 99% accurate. That means so much of your time, so much of matching between the reference signal and listening to all those sounds is saved just by these analysis. All right. So this is one thing, knowing the type of partial discharge we know, and the system knows, as it has got the standard waveforms with it, and it matches it over the time and gives you a result, saving a lot of your times. Now, second thing, the next thing is noise cancellation. As I was telling you, that just having some reference signal does not always help, because the kind of noise that is available in the substations is quite high. All right. Under those circumstances, you don't know when you are taking the reading what kind of noise you will get. So your system should be capable of identifying the noise also. As you can see over here, noise or external signal was identified by the system. And as you can see over here, the discharge energy that was taken is 100% of total power. That is, it is 100% noise, and the system is sure about it. So this is how good or how smart a system should be if you really want to do PD analysis with it, right? Next comes PRPD. Now, this is a very important term that is used for the analysis of partial discharges. This is a graph that you are seeing over here. PRPD basically stands for phase resolved partial discharges. Okay, this sinusoid is reference frequency of your system. Whatever frequency your system is working upon, or that particular equipment is working upon, I'll take that particular frequency only. Magnitude of voltage is not relevant. It is totally irrelevant over here. So that's why it is phase resolved. So I have a sinusoid. I have resolved this particular discharge pulses, or the discharge pulses that I'll be getting in terms of phase. So you have got a phase 0 to 360 degree. Now you have got 50 hertz of frequency, and the frequency that will be there, the discharges that you will be getting with reference to your phase, they'll keep on superimposing on each other. All right. It's not a discharge. It is not the signal that you captured over a period of 1 second or 2 seconds. Even if you take the reading in 5 minutes or 10 minutes, the superimposition will keep on happening. Okay, that's what actually phase resolved partial discharge means. That you have a system frequency reference, and then you are monitoring the clustering of discharges and the shape in which they have clustered. On the basis of which different type of partial discharges are monitored and are identified, as well as noise cancellation is done. this particular thing, although there is a standard IEC 60270, as you guys are very well aware of it, that particular standard has actually recommended and put that in their paper. This method was recommended in that paper only in IEC 60270, but that particular standard is applicable for online PD. But this analysis tool is very well applicable in online methods. With the help of it, the reason is, the help of it, you can easily identify the partial discharges as well as you can cancel the noise. Due to these reasons, you need to have PRPD in your system, in your PD measuring system. Now, you have got these terms as you are seeing over here, 3D mapping, as well as the PRPS, that is your phase resolved pulse sequence or your 3D mapping. Now, what does it denote is, suppose you have got this segregation or cluster of discharges here. Now, instead of putting them in a sinusoid and analyzing it, you basically analyze them in the cluster of the pulses. This is actually an advanced analysis tool that is given, that is available with the system. This is generally used with research labs or the labs that are, or the manufacturing units where behavior of a particular insulation system is monitored by physically or forcibly injecting partial discharges or simulating those partial discharges. So for that, this particular thing is quite useful. And as you keep on working on the system of basics of partial discharges, type of PD, as much you get acquainted with this, with the technology and the terminologies and how the analysis is done, this also comes quite easy to you, because here all you have to do is to not analyze whole discharges or all the discharges, just to take care of the particular clusters. Okay, so this is all about the 3D mapping. Next come PD Cloud. PD Cloud is a method, it is a technology available to segregate between more than one type of PD sources. Let's say you have got corona as well as surface discharge happening in an insulator, or you have got void as well as surface discharge happening in an insulator. Now you will be getting those signals. Those signals will be lying on your PRPD. Now your system should be smart enough. First, it should be smart enough to distinguish between these two PDs. But let's say it couldn't, because of noise or because of, it may happen that surface discharge has such a high magnitude as compared to void that system failed to identify that particular thing. So in that case, you have to take care of PD Expert, PD Cloud. So here, what you do, you again segregate, as this green box that you are seeing, you segregate actually various sources, and it is quite easy to use. Please, this might look intimidating to you, but it is quite easy to use. And you can easily segregate between different kind of PD sources if they are. So this is again one advanced tool available in the system. Now, you have got time of flight. Now, whenever we say we need to pinpoint the partial discharges or we need to localize the partial discharges, now what is the technology behind this localization? So this technology is called time of flight or time of travel. Now, what does that mean is, suppose this is actually a case study that we did. So here what we did, the internal UHF sensors were there, and inside that particular GIS, this is a case study of a 400 kV GIS, and inside that GIS somewhere, they had put some nuts and bolts, all right, without telling us. So this was done in a GIS factory, a manufacturer's unit. So everything was done in a controlled manner. So they had put these nuts and bolts inside the GIS chamber, and after that we were asked to do the PD localization as well as PD identification, where exactly that defect is lying, and we were not told about it. So after that, when we did it, as you can see, the pulses that you are seeing over here, they are almost of same kind here as well as here, irrespective of their magnitude. So what we basically do is, generally UHF signals, they travel at a velocity of propagation of 2/3 of speed of sound. That is, if it is a UHF signal, it mostly be traveling at 66.6% of C, that is speed of sound. Now, on the basis of the distance of that particular source from the immediate two sensors, we try to identify, okay, because there will always be a time of flight, that is a particular signal, depending upon the distance from a particular sensor. it will be detecting, or the sensor will be detecting that particular signal at a certain delay as compared to other one, right? Because the signal, these UHF signal are quite attenuating. They will always attenuate. Any signal will attenuate over the distance. So longer the distance, lesser will be the magnitude. So on the basis of that, we actually multiply VOP into T, and we identify the length of, or the distance of, that particular source from the 2 points, from the 2 sensors. So that particular principle of analysis is actually called time of flight or time of at the sensors from the PD source. Now comes product selection. You have got product mapping, as we saw. Now here you have got detection, measurement, localization, monitoring, and trending. Now we'll see exactly how to put into action, or how exactly to apply it physically. Now first one, as we saw in acoustic one, you have got this particular sensor that works in the acoustic range. So with the help of these various sensors, 124 number to be exact, you try to localize, detect, and identify the kind of PD that is happening. Second, you have got this particular solution where you can see this is a handheld kind of a product that has all the kind of sensors that we discussed. You have got your ultrasonic dish, as well as the TEV sensor and the coupling capacitor, as well as your HFCT to detect PDs, right? Now comes your surveying tool. This is a Dimlock 4. This is a surveying tool that is used for the substation surveying. Here you have got all the sensors. You have got 3 major channels, and they support all that is acoustic, HF, as well as UHF. So your acoustic sensors, your UHF sensors, the sensors that are already in the GIS or the external GIS UHF sensors, as well as your HFCT and your TEV. All the sensors are compatible with, and this particular system is compatible with the PD surveying. Next comes your PD specialist kit for acoustic system. So acoustic, as we discussed about, that acoustic is most recommended for power transformers. So here you have got 4 acoustic sensors and 1 HFCT sensor. HFCT sensor is for noise cancellation, and these 4 acoustic sensors are placed on the tank of this transformer. And with the help of time of arrival, the principle that we just discussed, we try to localize the partial discharge inside the transformer tank. So that is one of the most important aspect of this particular kit, that it does detection, measurement, localization, and monitoring and trending can be done. Next comes your, again, these are PD analyzers. This is 3-channel and 6-channel, but they work in HF as well as the UHF frequency ranges. The frequency ranges are software changeable, so you don't need to worry about that. So these 2 particular kits, as you are seeing here, they do all the purpose, just like the last one: detection, measurement, localization, monitoring, and trending. So as you are seeing over here, and as we discussed, it comes with the it comes with the sensor set, depending upon the kind of application that you have. Suppose you want to do the PD testing of your generator and motor, so you will require coupling capacitor. If you want to do PD testing or PD monitoring of your cable, so you will require RFCT. If you require PD testing of your GIS, if you have got internal UHF sensors, it is fine. If not, we have got external UHF sensors. So almost all the equipments are taken care of by these 2 kits. They are the same kits. It's just that it has got 3 channels. It has got 6 channels. The specialty of all the kits that we just saw is that they are all battery operated. So you don't need to worry about dragging a cable all around your substation. Now comes our monitoring systems. These are continuous monitoring systems. That is the sensors. So suppose this is a case. This is just a generic case. Suppose the sensors are there. Depending upon the kind of application that you have, just like we discussed, in cable you need RFCT, in a generator motor you need coupling capacitors, and in transformer you need either tap, 10 delta test tap kind of a sensor, or you can also use HFCT kind of sensors around the neutral winding, around the neutral bushing. So there you can have those inputs in these data acquisition units, and with the help of these units, they can form a chain of hundreds such units. That is 600 data points can be taken care of by one network, which can be monitored in the PC. So this is a monitoring system which detects and localizes the partial discharges. This is the 24/7 monitoring solution that we just discussed. Earlier one were the portable one. All right. So for all the equipments that you have, you can adopt this particular technology for your continuous monitoring. Now here is the product offering. Just this is one slide just to show the kind of product range that we have, just to interest you in that. So in case of power transformer, you have got your detector 3i, the kit that we saw right at the very beginning. Then you have got surveyor, that is your DIM block 4. Then you have got your analyzer. AR700 is an expert in transformer PD localization. Then comes your PD analyzer, that is a transformer diagnostics monitoring system. Same applies for instrument transformer. Everything is the same. Now the rotating machine, because they are almost same. They are inductive kind of transformers. Now you have got rotating machines. So in rotating machine, the principle of diagnostics is the same. So for surveying, you have got DIM block 4. For analyzer purpose, as we saw, that we have got PD analyzer. We can choose coupling capacitor or HFCT to detect the partial discharges in generator and motor. And for continuous monitoring, you have got PD analyzer, the structure that we saw in the last slide. So in the switchgear, you have got NL acoustics, the camera, the acoustic camera you saw. It can pinpoint by working in the frequency range, that is 2 kilohertz to 31 kilohertz. And also you have got DIM block 4 with the help of the UHF antenna. You can survey the whole substation switchyard without taking any shutdown or anything. Now, for continuous monitoring system, you have got PD map. This is one solution that works exactly like these, and you can monitor your whole system with the help of it. Then switchgear panel, you have got 3i as a detector. For surveyor, you have got DIM block 4, as it has got multiple channels, and you have got PD analyzer. All right. The analyzer, I mean, pinpoint of PD inside the switchgear panel can also be done with the help of PD analyzer. Or let's say a cable that is running inside the switchgear panels, or the insulator support insulators that you have inside the switchgear panels. So it can take care of it. Now you have got cable. So with the cable, again, we have 3i, DIM block 4 as a surveyor, analyzer for PD analyzer with RFCT or HFCT, and we have got PD analyzer, CDM, cable diagnostics monitoring system. All right, for continuous monitoring of cable. Now for GIS, we have got surveyor tool, DIM block 4. We don't exactly require detector, because when you are going with GIS, generally the solution that people ask for are the high-end solutions, because GIS is quite critical in that term. So you have got PD analyzer, 3 channel, 6 channel, with either UHF sensors already embedded or the external sensors that are provided with the kits. And you have got PD analyzer, GIS-DM. Okay, so with the help of which you can continuously monitor your GIS. So this is a complete solution that is provided, and this is a manufacturer specific solutions. But when you go out in the market, you will find solutions that are at par with the category that we have, categorization that we have done over here. So it is not like some monopoly kind of a thing. This solution is quite generic and available with almost everybody. And but we have a complete range for all the equipment. So this is the chart that signifies that. Now, this was everything that I had to discuss with you in this small session. This is everything that I could discuss. Now, as you are already aware,
Thank you, Jayant. Thanks for your detailing of the system and all other things. So, Jayant, there are a couple of questions people has asked.
Yes, sir.
If you go to the chat room,
yes, sir, I'm there.
Shit. So there, if you can, or I can ask you the questions in detail.
Yes, sir.
As Mr. Satya Sankar Sen, as very initial stage, he has asked whether PD is a continuous. So I can tell you, sir, PD is not at all a continuous process. So PD is an intermittent process. So PD can come and go. So if we want to really look for it, we have to wait for some time. We have to do the PD testing in several time, maybe in different load condition, different voltage condition, and different ambient condition, because if the temperature is too high and if it is having a thermal stress, then PD might be happening at a high temperature time, so it might be happening in the daytime when the ambient temperature is high. If because there is still that none of the researchers who has talked a lot about that PD, different types of partial discharge and other things. So they have never correlated anything like the PD can happen only at the high voltage time, or PD can happen only at the when the load is full, or something like that. So PD is not a continuous phenomena. That is the first thing we have to keep in our mind. We have to wait for the PD when it will happen. So if somebody is coming with a PD kit and doing the testing of the PD at your premises, and you are finding it the PD, you are lucky. But if you are not finding it, that doesn't mean that the kit is bad. So you have to understand, and if you are doubting that PD is there, so you have to wait for some time. You look forward for that thing, that device, for a over a period of time, maybe in different part of the day, maybe in the morning, afternoon, evening, night time. So all the things you can do a monitoring in several times, then there is a fair chance of you that you will be getting the PD. If you are getting the PD in always all the time, that means it is very serious condition, because partial discharge is the, by the name itself, it is a partial. So every time it is happening, that means the insulation condition is really going towards the bad shape. So you have to be more vigilant on that one. Similarly, Jayant, there are some other question that you can take couple of questions and you can answer. Uh, or should I
Okay,
read
sir.
that for you?
Yeah, please, you can read it to me because it will take me some time to go over there and find the questions.
Okay.
So if you're aware of
So
them, then I can.
there are a couple of questions which is asking about the correlation of PD and tan delta, or tan delta. How if I am measuring the PD, then whether tan delta is required, or vice versa, or sometimes whether can I get the PD is happening, that confirmation in some other test. So you have covered that part, that in part. So if you can elaborate that thing into detail.
Okay. I think what I got from you, sir, that what is the correlation between the tan delta values and the partial discharge? More or less, this is the question, I guess.
Yeah. So if I am doing the tan delta, do we require partial discharge, or vice
Of course,
versa, or the other
of
test
course.
like PGA with PD,
Yeah,
or
yeah.
infrared camera, infrared thermography with PD? So you can take it into a totality, so that
Got it, sir.
different questions from Mr. Abbas, Mr. Santosh Bhagade, and Mr. IS Indubhushan Srivastava, uh, and some more question from in the.
Okay, okay. Let me answer this, sir.
You can
Yeah.
take it in
Okay.
totality.
So, okay. So, in terms of, let's say, tan delta, or you can have whenever you are doing tan delta, you are having some values, right? Like you are, as per IEEE or IEC, you have been defined values like 0.9, or you have got this is the danger level above which, I mean, the insulation is gone. And when I say insulation, the insulation in totality is gone. You don't exactly know. Suppose you have got a cable is, let's say, 5 kilometers or 10 kilometers. When you are doing taking the tan delta value, you are taking the value of the whole cable at a point, not at a point. It is actually, you are taking a global reading, not a local reading, as you say, in terms of the cable fault location system, right? Now in terms of So I mean, the insulation, it's not like the insulation of whole 5 kilometers of cable is gone. It is just bad at a certain location, right? Now, for 10 delta, if you have already taken 10 delta, or people generally go with 10 delta, so once you have discovered that the value have either crossed 0.5, or it is anywhere between 0.5 to 0.9, it is critical only, right? Above 0.5, you have always be careful about what the value is. So there, when you go out there and do the 10 delta, you have got this value, but you will never know, be it bushing, be it cable, be it anything, where exactly is that defect line. For that, either you have to bring out your CFL tools, or you have to take care of, I think CFL tool is the only solution left with you to pinpoint the location. This is one of the features that I discussed in the very beginning, that this is the added advantage of partial discharges. One, you don't require an outage. Second, you will always be able to pinpoint the PD location. So if there is a PD at a certain point, okay, and the 10 delta is poor because of this, of course, 10 delta will always be poor due to the insulation degradation only. And with the help of PD, you can always identify it, what kind of defect is it. Out of the defects that we discussed, these are more or less the defects that will be possible in, let's say, your cable or any insulation available. Okay, so out of them, the type of PD that is there, as well as where exactly is the defect line. And most of the times, people generally, when the 10 delta value is poor, just to, you can say, just for a backup purpose, or just to corroborate their doubt that yeah, some insulation defect has happened. PD is not happened. Okay, just let me just complete it. That PD has happened. They come up with the partial. Okay, now PD on the whole is not a different phenomena than that of 10 delta. In 10 delta, it's just that the insulation is almost broken to a level. It has almost gotten damaged to a level that your IR has exceeded a certain level. So your IR by IC has gone bad. Whereas, I mean, it is.
So Jayant, in a nutshell, if we want to talk, that we can say categorize that PD is the cause of the reason, and as a result of the same, what we can see is the 10 delta value degradation, or might be DGA values will be coming bad. DGA results are coming bad, means gases will be more, and if there is a hotspot, that hotspot is the reason. One of the reason could be the PD. So we can conclude in that fashion, we can say.
Yes, sir, of course. You can always
Thank you,
say
Jayant.
this.
So there was another question asked by Mr. Ankur Sangavan. His question was that can we retrofit the PD sensors in existing GIS switchgear panels? So, sir, yes, it is possible. It is very much possible. Retrofitting is two ways. One is that condition is that you do not have any sensors installed into the GIS. That could be probability one. Second probability could be that you have the installed sensor, but that has gone bad. So the chances of second case is very less. So I am considering the you do not have the sensors installed in your GIS. So in that case, yes, we can install the external sensors, as we have told during the presentation. Those are the AES type of sensors. Those are externally which can be fitted into the GIS, and it is the UHF type of sensor, so those can be used. There is one more question from the cable PD measurement, Jan. Why HFCT is majorly used or preferred? If you can highlight once again the same.
Sir, in terms of cable, generally the method of analyzing or detection of partial discharge is that whenever there is a defect, those defects or the partial discharge current or PD current or PD voltage due to that, that particular physical defect will always, these PD current will always run through the sheath one way or another. Okay, even after coming to the cable. So the chances that if there is a partial discharge, then the PD current will definitely be flowing through the sheath, and most of the times near the terminations or at points at more than one points, generally these terminations are grounded, right? The sheath of these terminations are grounded. Now, these currents, these PD currents, they always try to flow down to the ground, as we have seen earlier in the case of TEB or other PD defects. Now, when we put our HFCT across these cables that ground the sheath of our cable, the chances are there that you will always capture the partial discharges that will try to, the partial discharge current that will try to flow to the ground. So
Okay.
that's why HFCT is used over there, and there is no chance of using as these are high frequency pulses. So the noise coming from your system harmonics or your zero sequence current and everything is nil when it comes to HFCT. So this is the application of HFCT in terms of partial discharge measurement.
Okay. So I believe, Jayant, you have covered the subject pretty well, and though you have taken gone a bit first in the product selection or product mapping zone, there once again before closing, I want to tell you all the participants to whatever the PD solution you are going for it, what you need to see is that what is the frequency range it is working, or the frequency band, whether it is acoustic or ultrasound, or it is HF or UHF, or it is the VHF or the TEV sensors, and what are the sensors the company is supplying. That are the two major things. From that one only, you correlate that what are the devices for which you can do the measurement of PD. Those are the two basic factors. And the third factor, what Jayant has highlighted to you, is that okay, you see the type of the product, whether it is a PD detector, or it is a PD analyzer, or it is a PD measurement kit, bare measurement of the PD level and type, that's all only, or it is a PD localization. So based on that, so when it is a PD localization, that means you should have more than one channel. You should not ask, okay, I require a single PD kit for every object of the thing, and all will be continuously monitored. So it has to be, it cannot be possible when it is continuous monitoring. So there is a specific application as Jayant has shown. So for GIS there is different, for transformer that is different, and for generator or for motor continuous monitoring that is different. So in that fashion you have to be very careful while selecting the PD product, as it has been shown that the product category, whether it is measurement or only analysis, or the total pinpointing, or 24/7 monitoring. So that is the first thing. Second thing is the what are the sensors the supplier is going to give you in the as a total package, or if they are not giving the types of suppliers you require, so you have to add the prices, you have to take purchase all the things. So you should not feel deprived that yes, I have taken a big kit, but it is having so many features, but it is not it cannot, because I have to purchase so many other things. So you have to be very careful on that one. So in short, thanks a lot, Jan. Thanks for sharing your experience and other things. And to all the people present, we like to thank all of you in this different difficult time of Corona, and joining us in this to make us a huge success. If you require any further information on the technical queries, you can write to us as mentioned in the screen. If there is any after sales related information you require for any of our products, or you can contact our service team. And for the product or detailed information, you can contact our marketing team. And for the people who are asking, can we see the video again? Yes, it is very much possible In the same link, you will be getting the video once this session is over. So thank you very much. Thanks to all of you for joining us. Good evening. Good night. Have a good time. See you all tomorrow.